Welcome final year electrical engineering students. All right, let's dive straight into this explainer and demystify your brand new syllabus. You're about to tackle course 2306402B, Design of Power Electronic Converters. And look, this isn't just another dry theory class. It's the actual bridge between the concepts you've been learning for years and the physical, high-tech hardware you're going to be building out there in the real world. What we're checking out today is the official course handout straight from the Department of Electrical Engineering at the KK Institute for Semester 7, Pattern 2023. This document, it's basically your entire roadmap for the semester. We're going to break it down so you know exactly what to expect, how to succeed, and what modern tools you'll be using to get there.
Here is how we'll break down your journey today. First, the foundation. Second, earning your marks. Third, the 5 core units. And finally, modern tools and AI. Let's jump in.
Section 1, the foundation, building your engineering blueprint. Right off the bat, a crucial detail to know is that this course carries a solid weight of 3 credits, demanding 3 hours of theory every single week. This means it is a major, core component of your final year education. You're really going to need to lean into this one, because it builds directly on your prerequisite knowledge of basic power electronics. So why this course? Well, this quote directly from the syllabus objectives hits the nail on the head. The goal is to empower students to design advanced power electronics converters for a given application. You're not just trying to pass a test here. The ultimate objective is to give you the practical chops to start with a totally blank piece of paper and end up with a fully specified, advanced converter for a real-world scenario. You are officially shifting from a student mindset to a full-on design engineer mindset. Section 2, Evaluation, Earning Your Marks. Now, let's talk about the grading. You're designing for a total of 100 marks, and that's split into 2 main buckets. 60 of those marks will come from your end semester exam, which obviously assesses your overall comprehension. But the remaining 40 marks, those come from your Continuous Comprehensive Evaluation, or CCE, meaning your consistent, week-to-week effort is going to be highly rewarded here. And here is exactly how those 40 CCE marks are carved up. They're evenly split into 4 10-mark slices. You've got Assignment 1, based on the first 2 units, and Assignment 2 covering the rest. Then come the LMS tests. And actually, I love this detail. It's based on your best 5 scores out of a minimum of 10 sessions. So you have some wiggle room. Finally, you get 10 marks dedicated to solving a case study or applying a teacher-defined tool. It's a super balanced, really practical approach to grading. Section 3, the 5 core units, assembling the blueprint. Okay, think of the syllabus not as just some boring list of topics to memorize, but as a sequential 5-step journey to designing a working converter from absolute scratch. First, you start with the core mathematical analysis, then you move on to picking your silicon, next you build the protective and driving circuitry, manage the physical heat and magnetics, and finally, you package the whole shebang onto a clean, interference-free circuit board. In Unit 1, you establish your core analysis. This is where you lay down that heavy mathematical foundation. You'll be diving deep into the analysis of buck converters and H-bridges, comparing bipolar versus unipolar pulse width modulation. And, absolutely crucial here, you're going to learn the exact design equations needed to properly size up your inductors and capacitors for specific examples. This is literally your theoretical bedrock. Moving on to Unit 2, things start getting physical. It is all about component selection. I mean, you can't design a converter if you don't understand your switches, right? So you'll learn how to decode those often incredibly dense switching characteristics and real-world datasheets for power diodes, MOSFETs, and IGBTs. The syllabus heavily emphasizes looking at real datasheet examples, which means you'll be reading these specs exactly like a pro engineer does when they're sourcing parts. Now, Unit 3 is all about protecting and commanding your circuit. Those beefy semiconductors from Unit 2, they need precise instructions on when to turn on and off, and they desperately need protection from nasty voltage spikes. So here you'll dive into gate driver requirements, exploring optocoupler and pulse transformer-based designs. Then you'll tackle snubbers, specifically analyzing underdamped, overdamped, and critically damped RC and RCD snubber designs just to keep your entire circuit from self-destructing. Unit 4 forces you to deal with the unavoidable physics of power electronics, heat and magnetism. Because, let's face it, a converter that works perfectly on paper but literally melts on the test bench is a failed design. You are going to learn thermal modeling and how to properly select heat sinks to dissipate those power losses. On top of that, you'll study magnetic core materials and actually execute a custom transformer design from scratch.
Finally, we hit Unit 5, which is where you assemble the physical hardware. You've got the perfect schematic, but now you've got to make it real. This unit covers a massive industry challenge, electromagnetic interference, or EMI. You'll study common mode and differential mode noise and design your own EMI filters. The whole thing wraps up with PCB design principles, where you take all the components you've selected and arrange them optimally on a printed circuit board.
Section 4, the modern edge, AI, and software tools. Now, as a modern engineer, you're obviously not going to be designing in the dark or relying just on hand calculations. This course integrates essential, industry-standard software right into the curriculum. You're going to master core simulation platforms like MATLAB Online and LT-SPICE, so you can verify your designs before you even think about building them. And for creating your schematics and hardware layouts, you'll use accessible but super powerful PCB design tools like KiCad and EasyEDA.
But here's what is truly groundbreaking about this syllabus: the direct integration of artificial intelligence into every single unit. Just take a look at this breakdown. In Unit 1, you can use AI for converter sizing and duty ratio validation. Unit 2, AI-assisted datasheet interpretation, which is going to save you hours of reading, trust me. By Unit 5, you're using AI for EMI diagnosis and PCB layout recommendations. Basically, AI is being treated as your ultimate engineering power-up throughout the entire semester.
To make this happen, the handout actually explicitly lists the AI assistants you're encouraged to use: ChatGPT, Google Gemini, and Perplexity AI. And you'll use these generative AI tools right alongside professional component selectors from companies like Infineon, DigiKey, and Mouser Electronics. This exact blend of traditional engineering rigor with cutting-edge AI assistance is exactly how top-tier engineering firms are operating right now. Ultimately, this course bridges the gap from classroom theory to high-tech industry reality. You have the exact roadmap, you know the grading metrics, and you have an incredible suite of modern AI and simulation software in your toolkit. So the final question you got to ask yourself before the semester kicks off is, with all these tools at your fingertips, what kind of power converter are you going to design first? Thanks so much for joining me on this explainer, and good luck with your designs.